Okay, hey everyone. Welcome to another graduate seminar. This is Zach, also known as Zacharias Maximus. He's giving a talk on an introduction to modules. We also have some light entertainment for you guys. So enjoy and good luck.
Calm my nerves. Now I have to fix it. You think that's good? Okay. All right. So, many of us are familiar with linear algebra. It's a very ubiquitous subject in math. And the central object of study there is vector spaces. And we like to study vector spaces and linear transformations between them, subspaces and whatnot. So today I'm going to talk about a slight generalization of vector spaces, where instead of having a field of scalars, we take a ring of scalars. And we'll see how that changes things and how some things are the same. I'll just go ahead and write down the definition. So first, so from now on, every time I talk about a ring, we'll assume it's a commutative ring with unity. So we start with a commutative ring with unity, and then we say that an abelian group, and what we want is a function that I will denote with this little dot here, m, such that this function satisfies a few properties. So number one will be that the identity behaves as we'd hope it to. It does not affect the elements. Number two is we want a sort of associativity, and these are sort of like the axioms for a group action. I'll remind you, the third and the fourth deal with distributivity because we have two different addition operations and then one multiplication in the ring, so we want everything to work together nicely. So first we will say that we have this, so this is going to be the addition in the ring, and this is the addition in the group, so maybe it's worth writing a little r there. Normally, we will do this juxtaposed multiplication for multiplication in the ring, and this dot, we'll try to keep writing the dot to make sure that we know that it is this function. We're acting on an element of M by an element of R. And then we have the last one, is another, we want to be able to distribute over the group operation of addition. So if we have an abelian group, a ring, and a function like this, then this is a module. This is the structure of a module. And you'll notice that it's actually the exact same as a vector space. The only thing that we've changed is that instead of our scalars coming from a field, they come from a ring. But starting with an abelian group and adding these things is the exact same thing. So, a few examples. So if we just take this function to be multiplication in a ring on the left, we get that every ring has a very natural structure as a module over itself. So that's an obvious example, and that's one of the reasons that they're important, because they're very connected to rings, and you care about rings sometimes. So another obvious example is that any vector space over a field is also going to have a modular structure, because if K is a field, then in particular it's a ring. So again, we have the exact same thing. And last example, an abelian group G over the integers G with this. So if we take any abelian group G, letting G be in the right, then this action is just repeated application of the group operation, and this always gives us a module structure. And in fact, every abelian group can be given this. Every Z module is also just exactly an abelian group, because we've started with an abelian group. So those are some simple examples. So next, and these are mostly going to be things that are standard across all algebraic structures, but I'm just going to write them because it's important. We have these objects now. Now we want to talk about maps between them, and we want those maps to have some nice structure. So next, we'll talk about module homomorphisms. So if we have that M and N are R modules, so we want to talk about homomorphisms between modules over the same ring, generally the case with vector spaces too. And we have a function f from M to N. We say f is module f if, I'll write the quantifiers over here. So it's just the standard linearity that is also the exact same as, so it's what you would expect. It's a linear map between modules in the same way. We want linear maps between vector spaces. It can take out scalars, and it has the additive property. So next, another standard definition for whatever algebraic structure, submodules. So say M and R modules. So we have, again, two R modules, and this time we want that the abelian group structure, we have a subgroup, that N as an abelian group is a subgroup of M as an abelian group, and R times N if it's closed under scalar multiplication, then that's not supposed to be a period. Is this true? Then we say that N is a submodule of M. So that's the same as subspaces. However, there are a few differences, because now that we're in rings, we have one example of submodules that we don't get for vector spaces. So if I have any ideal of this ring R, so we say I ideal, right? Then we know from definition of an ideal, it is a subgroup, the additive structure, and it's closed under multiplication by elements in R. If we take ideal, then I is going to be, if we take R to be an R module, then we can think of I as a submodule of that. Since fields don't have non-trivial ideals, this is not something we get in a field. So that's one of the differences. Now, I think the last just standard algebraic structure definition, we want to take quotients of modules. So now that we have this idea of a submodule, we might want to quotient out. So if we say,
Again, if we remember linear algebra, it's going to look very similar.
it's going to look pretty much the same, yeah. I'll write it for, completion. And I'll use this to, I should have written it there, but this will denote submodule of less than or equal to. Then the quotient structure, we can construct the quotient module over n, which is just going to be exactly what you would imagine. It's going to be the set of all cosets. These cosets will be constructed in the same way they would be constructed if we just considered them as abelian groups. And you notice, since they're abelian groups, this n is guaranteed to be a normal subgroup. So we know that this construction makes sense for addition, and it turns out that it also makes the same sense if you give it the obvious R module structure, where R acting on this is just R acting on a representative of the coset. So we can take quotients, which is nice. And that actually gives us another example of an R module, where any quotient of R by any ideal will also automatically have an R module structure, just because of this. If we think, from this example here, I and R are both R modules. We quotient, we get another R module, which is also something that we don't have in fields because we don't have ideals to quotient by. And now, real quick, something that's important to mention is generating sets. So these work the same as for pretty much anything. That's the worst G of all time. So if we have some collection of I should start. So if we start with some R module, and then we take some collection xi, some collection of elements from that R module, and then we can write everything as a sum we can write everything as some linear combination, actually finite linear combination. So in this case, we restrict J to be finite. If we can write all elements of this module as finite linear combinations of these xi's, then let's see, if, I should have written an if there, huh? Then we say this, I'll call it A. I should have given this we'll call this collection A. So I don't have to write it again. We say that A generates M. And in particular, if this set does not have any, if they're linearly independent, so if we can't write 0 as a non-trivial combination of these things, then we call that a basis. And here we get to one of the biggest differences between modules and vector spaces, and that is that not all modules have a basis. So I'll write it up here. Not all modules. All modules have bases. So as an example, we could try to find a basis for Q as a Z module. So we want to find some set that, sort of spans Q with Z linear combinations, but also does not have any of those linear, I didn't write it there, I don't know why I put it, does not have any of those linear dependence relations. So just the quick way to show this, we can sort of immediately see that it has to be more than one element. Q isn't cyclic, so we have to have more than one element there. So our generating set might look something like this, and it could be finite or infinite, but we just need 2 elements. But as soon as we have 2 elements, we can write out some linear combination of them. This is supposed to be dot plus. We can write out some linear combination of them, and then just quickly manipulating the things. We can write this as PS over QS. Right, just rational numbers. You can sort of multiply the top and the bottom by the same thing. And then if we let n be equal to RQ and n be equal to PS, we have a non-trivial linear combination that would give us RQ times PS. M equal to negative PS. Right, and these are the same by commutativity of multiplication. So this equals 0, and then we found a non-trivial combination. And maybe I should have pointed out at the start, we're going to assume that P and R are non-zero, because 0 isn't going to generate anything. So
why do we have to do the top and bottom by S?
because they have different denominators. So I wanted to make, is there a better way to do it? Maybe.
Could you make M equal to QR and then M equal to SP?
Oh yeah, probably, yeah.
Negative.
Yeah, well then that might be a faster way to do it, yeah. This was the way that I thought of. So, but yeah, you could just do that. Either way, we come to this conclusion, which means that Q is not going to have a basis as a Z module, which is, strange compared to vector spaces. And another example is just, let's see, we could take a finite abelian group. GA finite abelian group over Z as a Z module. Then for any generating set, we would have, I guess I should probably, a finite non-cyclic abelian group. Because if it was cyclic, then we would have a unique way to represent 0. But if we have some generating set, G1, G2, blah, 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 then these elements are going to have finite order. So we can always act on them, G1, say G1 M plus G2. And we can use basically any multiples, whatever order G1 and G2 have, we can just act on it by multiples of that. We get a bunch of different ways to represent 0, which is exactly what we don't want. So
That means defining morphisms is kind of hard because you have to care about
exactly.
these relations.
Yeah. So now I will talk for a second about a class of modules that does. Can I use this part? Should I not go over here? Okay, just not the bottom? Okay, yeah, sure. Okay, that's fine then. So now I will talk about a class of modules with bases, and we'll see what the consequences for that are. So free modules are modules with bases. That's we say, let's see, M and R module. If either of the following are true. So we can either have that M has a basis, or M is isomorphic to a bunch of copies of R. So that tells you that if a module has a basis, then it's actually very restricted in what it can be. It can be exactly a bunch of copies of R direct sum together. And you can sort of see why this would be true. If you have this isomorphism, wherever we're mapping the canonical basis for this, we can always pick a basis for this that's the identity of R in one coordinate and 0 everywhere else. If we'll map that somewhere in M, and that should be our basis for M, because we can't have any linear dependence relations over here that don't go back through that isomorphism. And if M has a basis, then we can just have each one of those represent one of the copies of R, direct sum a bunch of them together, and then we'll find that isomorphism very easily. So so it's, tells you something about what happens when you have a basis, that it's exactly this. So interesting. So now we will go back to some similarities between modules and vector spaces. So one theorem that many of us are familiar with in linear algebra is the Cayley-Hamilton theorem. Every matrix is going to be a root to its characteristic polynomial. We have an analog of that for modules, and it's a little bit, the statement is maybe a little longer because there's more that you can say about it, which we'll see when I write it down. Let me make sure. Yeah, sure, okay. So we start with a finitely generated R module and an ideal of R. And then we have a module homomorphism, that's not the end of the sentence, such that is contained in I times M. So whatever we get from taking products, things in I, things in M, we say that the image of phi is in there. Those are our assumptions. And then we get a sort of satisfies this equation, which is a lot like is a polynomial in phi. This important thing with AI all being in this ideal. So if we were taking M to be a vector space, then we would either have I as the zero ideal, which means that this is the zero map. So it's not hard to find a equation like that that it satisfies. Or we would have that I as the whole thing, and then we would just get that these are in they're scalars, right? They're in the field. But since we have ideals, there's a little bit more, whatever you want to call it, wiggle room maybe.
So this statement is there is an equation, but it's not.
Yeah.
Say specifically what the conditions are.
The proof does construct it. Yeah. So it satisfies just an equation. We'll see what it is at the end. Yeah. And the proof isn't too bad, so I will do it. So first off, we pick we just call this our generating set. We assume that it was finally generated. So we have this. Then since this is a generating set, we can write the image of any of them as a linear combination of other ones. And specifically, because of this condition right here, we can guarantee that these are in I. Ij is in I. So we can write it as a linear combination with coefficients in I. Now, we can write this, we're indexing over two things. So it'd be natural to write this as sort of a matrix, where over here we're going to have, I guess I should write, then write, so we have this row vector, column vector of all of our is going to be equal to some big matrix of these coefficients. Blah, blah, blah. So that's what this gives us. Now we want to move some things over. So first I'll do that. I want to write this as, let's see, x1, just on the same side. Minus this whole thing. Times this. Equals 0. And I will write it as the 0 vector because it is a column with a bunch of zeros, and that'll be important later. So now I want to write this as just one matrix times just one thing. And I will just write down what it is, and then I can justify why it makes sense. Opposite. And then we'll have phi minus and then right there times this. So writing it like this, you can sort of see if you just did the multiplication, we would have sort of distributive property. Maybe the weird thing is mixing the subtraction of maps with elements, but
each element determines a linear map.
Exactly. Each element determines, just by left multiplication, you get that each element is a linear map. So it's, sort of fine to write it all like this. And when we have it like this, and I will, also, one thing to note that I forgot to say, these A's are not the same as these A's. I should have made them B's, but I forgot to. Or these B's, I don't know. I'm going to call this big matrix B. And then we're going to go over here. Now, what I want to do is multiply on the left, on both sides, by the adjoint of B. So that's going to give us B times B times this equals still 0, because, by 0. So the adjoint of B times B, one property of the adjoint is that this product is going to just be a matrix, the identity matrix times the determinant of B, or just the determinant of B down the diagonal. So we will end up with B, B, and then a bunch of zeros everywhere else, times equals 0. So what this tells us is that this determinant B annihilates every single one of our xi's, because this is going to be, this multiplication is going to give us a column of zeros. So all of these are going to go to 0, which also tells us that this step B must annihilate every element in the module, because we can write every element as some linear combination of these. So then applying whatever this is, which, we're thinking about it as a morphism, as a homomorphism, because it's phi, as a phi in there. And the elements is just left multiplication. Gives us that det B is the zero homomorphism in this module, from this module to itself. So whatever that ends up being, which might be very complicated depending on what our A's are, we can sort of immediately see that it's going to be powers of phi times coefficients in this ideal, because it's closed. The ideal is closed under multiplication and addition. So, might have to do a lot of grouping, but eventually we will end up with whatever determinant B, right, is 0. As the 0 as a map, it's 0. So, that's the proof. And again, in the vector space case, it just gives you that whatever this phi is, this phi, be represented as a matrix, and that satisfies this characteristic polynomial, which sort of similar computation to that. We have 25 minutes left. Going a lot faster than last time. Let's see, I can go here next. So I definitely have like 25 minutes left. Yeah, so next thing I will say is just quickly, I will prove one form of Nakayama's lemma. It's very important in commutative algebra where we study modules, and it's very easy to show one of the forms of it after we have this. So, thought it would be nice.
And since it's a lemma, it's proved, you prove other important results. Do you happen to know what any of those are off the top of your head?
Could I prove anything? Oh, yeah. Bryce asked if I know any of the important results off the top of my head that use Nakayama's lemma. I'm not sure that I would be able to present one right now, with the stuff that we've done so far. But I'll keep thinking. So let's see, the statement of this is this specific.
If I remember correctly, algebra version, or the finite version of
Finite field version of Riemann-Roch theorem. There you go. If only I knew how to prove it.
also used to prove a version of the inverse function theorem in algebraic geometry.
Oh yeah, there's some of the statements have to do with things like that, where you have a basis of a quotient module. You can go up to a generating set for the module. But that, I don't know if that's a theorem as much as a different statement of the lemma. But yeah. So the statement of this is going to start somewhere the other one we want. M is a finitely generated R module, and then I is going to be an ideal R. So if we have these conditions, then there's some x in the module where it's equal to exactly 1 mod this ideal, and it annihilates the whole module. And the proof for this is that we just take the map. Where did I write the thing? Yeah, I wrote it over there. So we want to take this phi in here just to be the identity map. So I didn't name that, but I'll just say take identity map. Just from M to M. Take phi in the last theorem to be the identity map specifically. Then that gives us some equation like that where we're going to have, all right, 1 times phi to the n plus a0. Then these a0s are going to be in the ideal. A0 is an I. And all of these phi's are the identity maps, so they're just going to go away. And we're going to be left with something that says a map, if we treat just 1 plus n minus 1 plus this as a map is going to be the 0 map. And you can sort of immediately see that modding it by I will remove all of these a's because they are exactly elements of I, and we'll be left with 1. And that is the statement of that. I don't think there's anything that I could present right now, unfortunately, proof for it. But my reasoning for doing it was just that it came so easily from that thing, and it's a important thing.
When was Napoleon approved?
When 50s sounds maybe a little later. Maybe a little later.
Okay. X is an element.
Yeah, X is an element of X. No, X would be an let's see, X is equal to 1. Yeah, because we want it to be 1 mod I, right? And then it's this sort of multiplication. So yeah, yeah. Did I say it's an M? Oh yeah, my bad. Oopsies. Yeah, that doesn't make sense. You can't multiply.
until the proof was done to see
Oh, no, yeah, no, that's my fault. Because, yeah, you're going to be multiplying it here, so it's makes sense as a... All right, let's see. All right, the last thing that I have, if we went a little faster than I expected, is something that is familiar from group theory instead of from vector spaces. And there are a few...
By the way, Zach, going overboard is the only thing. You're applying it to see.
Okay, I think I can just talk about this for a second, but then after that I don't have anything else prepared. Oh, do you have?
Should that be some x in R which is not equal to 1? It's very clearly.
Um,
Do that.
1?
Oh, and is equal to 0. So yeah,
Yeah,
Sorry,
yeah.
okay.
Yeah, no problem. Yeah. Okay, so the last thing, when modules are over sufficiently nice rings, sometimes we get very nice theorems. So if we restrict our ring to being a principal ideal domain, then we have a decomposition. Maybe I should say, first I'll just write for a second what a primary ideal is, because it comes up in the definition of this, but it's not there. Primary ideal. So, ideal, jeez. If So it's a lot like the definition of a prime ideal. We just take power. So it's like a prime power ideal sort of thing. And it'll make sense in a second why that's the case. So this thing, yeah. Yes, okay. I can write it right here. So this is one of the, sometimes called the structure theorem for finitely generated modules over a principal ideal domain. So if we take, I'll write theorem first. And I won't be proving this one because it's more involved, I think. So first we want to start with M of finitely generated. A finitely generated R module for some principal ideal domain R, which is just every ideal is generated by a single element. Then we can write M, then M, let's see.
Sorry, wait. R being a PIT is part of your hypothesis?
Yes. A generated R module with R at P. Then decomposition where I so we get this decomposition where we have primary ideals and these things that generate them, we know that there's one element because we're in a principal ideal domain. We can say that these are unique up to multiplication by an invertible element of the ring. So now with this, we can notice that if we take, I guess I can write sort of example in a sense. A finitely generated abelian group. Oops. Group. So if we take M to just be a finitely generated abelian group over the integers, then we will get that M is isomorphic to some is of Z over this PI, where these PIs are primary ideals. So in the integers, this just gives us prime powers, and this is exactly the fundamental theorem, finitely generated abelian groups. So that's pretty neat. We have a little bit of a generalization of that when we take modules over a principal ideal domain. So that's pretty much all that I have prepared for today.